Welcome to the 5-day MTP on image fusion techniques and applications for enhanced applications using image fusion. And today our speaker here, Dr. Sree, Associate Professor, CVR College of Engineering. Today, ma'am is here to present a session on principal component analysis for fusion. I request Nara sir to present a topic. Welcome. Coming to the speaker details, ma'am pursued the BE from PCA College and pursued ME in SSP Signal Processing and PhD from the Osmania University. And ma'am, research area is on post illumination and blur invariant based recognition using ML algorithms. And ma'am is having the 20 years of teaching experience and 3 years in the research experience, and handled the 3 projects, one from the analog devices India and 2 from new generation. And ma'am published various journals like 15 international journals. We welcome you, ma'am, for the session, and I request ma'am to take over the session for this topic. Thank you. కొంచెం దగ్గరికి చెప్పు.
Good morning, everyone. I'm very much thankful to all the faculty for choosing me to present a lecture on image fusion. I'm Dr. Hema Sree. I'm basically done my PhD from Osmania University. And my area of interest is purely on image processing and working with machine learning algorithms, work with BNN and CNN. As my today's topic was given as principal component analysis for fusion. So before going to the image actual topic of the principal component analysis, I want to share some particular important concepts regarding to the fusion. Some definitions are already discussed by different speakers, but at a glance, I need some continuity. I just take few points. So basically, image fusion generally we define as it is a complementary information and removal of redundancy from multimodal images to obtain the relevant information to form a single or a hybrid image. So as we are taking the image from 2 different sensors, what is required part we are grabbing it, unwanted part we are just deleting it. So I can just say image fusion, fusing image. So generally fusion we say as a union of different things, byte or as byte it is melting, and imaging making a representation or imitation of an object. So finally, image fusing or fusion imaging we define as set of methods. So not only one method, we are having different set of methods, tools, and we are using data from 2 or more different images to improve the quality of the information. So ultimately, I want to improve the quality. And what is that quality also? We just have a look. So image fusion, several definitions we can able to define it as it integrates information from multi-image sensors data such that new image data is obtained, which is more usable for the further processing task. And it can be described as collection of low or bandpass copies of an original image in which both the band limit and sample density are reduced in regular steps. And this is the main part which we use in the remote sensing applications. We usually follow this type of terminology, that is high spatial and high spectral resolution required in a single sample. So most of the available equipment is not capable of providing such data, especially for satellite images. We are having different cameras will be grabbing different images. So what is required, like we are having pan images or MS images. So we integrate such that we can go for further processing, getting the spatial and spectral resolutions characteristics. And why fuse? So there is a question that we had image fusion, but of course, we had defined the definition, but what is the requirement of fusing? So here that sharpen the image resolution, that is for the display purpose, and improve the classification and other. Classification in the sense, we are acquiring the images by the camera or different sensors, but after acquiring that one, that information may be in the proper manner or what is required. We may be having blur in the images or some part of the image may be lost. So what we'll do is 2-3 images, we'll just combine it and acquire the required information. From first image, I'll take some part of the image which is required for me. From the second part, I'll take another image. Like that, I'll just take the required information, what is needed for me, so that I just turn improved classification. For example, as I told, face recognition. So it's just my research topic. So I'll take different faces, but when I'm taking the photograph of the faces, one face may be frontal. Some, when I'm just taking a photograph as she's taking, we may be having some shaking. So blur may be imparted in that particular image only. Another image, I may change my position of my face to the other particular part. But when I'm just going for recognition, so all the things which I'm just making into frontal face, and if my particular part is rotated or if it is recreated with some particular blur, each image has to be modified with some particular measurements. What are those measurements also I'll let you know. So once all these particular parts, if I use it in the proper manner, I can classify this person is belonging to Hema Sree or this person is belonging to some X person. I can go for the classification. So that is the main part, improved classification. If otherwise signpost is there, I may predict that I may be Hema Sree, but somebody says that they may be X person. So misclassification may be obtained if I'm not fusing the images properly. So not only sharpening, for classification also, this works a lot. What is the main goal of the image fusion? So as I just mentioned, higher spatial information in one band with higher spectral information in another data set to create synthetic, higher resolution multispectral data sets and images. We go for synthetic because we are generating it. Original images, we are taking it and we are modifying that particular data and we are generating a new image. That's why the name is given as synthetic images. Generally, generative adhesive network, GANs, is the topic which we are dealing in the later scenario. GANs, generally we use these type of techniques to obtain the synthetic images. Or whenever our data sets are very less and we want to improve the data sets so that classification becomes more easier, I go for the synthetic images. So if we just observe a simple example, so this is some of the satellite image taking panchromatic image and multispectral image. This is from one sensor, pan images and MS images. But if you just observe the data, here we had some part of the image and here another part of the image. So some part of the image I'll take from PN and some part of the image and combined with the fused image will have the complete information. So some cases the background may be lost. Some cases the building's identity sharpening may be lost. Combining these two images, we obtain the fused image. So whenever I'm fusing, what are the general requirements imposed on the fusion result? To obtain a perfect fusion, what I have to do? First of all, first step is preserve all the relevant information contained in the source images. First of all, from the sensor, take the complete information what you can take it. And fusion process should not introduce any artifacts or inconsistency. Whenever you are just taking, by your methodology, you are yourself don't introduce any extra information from your side. What is that? Grab it. But don't put extra information in the thing. And this is more important. when we are using our fusion techniques, don't introduce a noise. It should be noise free and irrelevant features. First of all, background is plain, but unnecessary we are introducing background with some particular flowers, which is irrelevant information for us in some particular applications. So that irrelevant features and noise should be suppressed at maximum extent. So when we are implementing the fusion process, we should take care of this particular scenario. And main applications starts with remote sensing, medical imaging, automated machine vision, and aviation, so on. And now, so image fusion is a part of image registration. So registration, representation, these are very important scenario in image processing applications. So as image fusion itself is a part of registration, we can say. So process of overlaying two or more images of same size and orientation. Here I'm more particular with size and orientation. So same time, different sensors, we are viewing it at different time. So whenever I'm just taking the fusion, a single image from different sensors, I can be able to grab it, or the same image. If I consider a medical image, today I'll be just have a medical image of some X-ray image of some lung. After 10 days, maybe lungs are affected some particular because of cold. Some will have some phlegm in the lungs. After 10 days, the same image of the same location will be identified that whether the phlegm has removed or not. So that is at different time. And which I just given the photograph of the sensor, like when I'm taking a satellite image, the same image from different sensors is the first fusion. Second one is image at different time of the same person or same scenario. So a simple example is our human body where our brain itself, how it acts, we are having two eyes. Whatever we are seeing is a single image. So two sensors are nothing but two eyes. So through the eye, we are registering. Actually, we are undergoing the fusion technique within ourselves. So the final purpose is image fusion. I can say that it improves the information extraction. This is a very typical example which I found it is the best one. That is, we had just taken some X-ray image and from like taking the tumor PT scan, PET scan will say that, okay, in that PET scan, I'll just identify the particular part of the kidneys and liver functioning part. So when these two are fused and the yellow color is there, the tumor part is identified. So this is the original image. When it is merged with that particular another PET scan image, you can able to identify, especially in medical applications, as we can able to identify different types of problems so that solutions can be revealed. And what is the need for image registration? So when I'm going for the fusion techniques, we are saying fusion, mixing of the two images or three images like that, everything we are mentioning it. But when I'm taking two images, what care we have to do? Okay, I had taken two images, I performed some particular algorithm, but output we are not getting it. What is the reason? What is the background? That is, before doing the fusion process, we have to go with some particular pre-processing technique. What is that pre-processing? Is not the pre-processing, it's our observation. How to take the data, how to place the data. Can you just guess what is that 4 different blocks I had mentioned, no? For what sake I had given this one? Can you guess? Yeah, misalignment. Any more? Yeah, as ma'am said, there's a misalignment. Actually, I want to fuse these two images. So if I take these two images, can we get a proper fused image? Naturally, no, because my axis, whenever I take an image, you know very well that ours are pixels with range of n by n, 128 by 128. So the pixel location of this point is completely different with the pixel location. Then so here we are not having a proper alignment. So whenever these type of images are fused, first and foremost thing is that I had to go for some transformation techniques as we studied in our image processing. I have to index this particular position to the index this particular position. Naturally, whenever we are taking the photographs, our indexing is not perfect because two different images I'll take from two different cameras. I may get different types of photographs in this way. So we had to go for geometrical transformations. And this is the part where we are having some slight slant rotation, and this is completely slit as well as your size is reduced. So my image is size of 512 by 512. The second image size is of 128 by 128. So naturally, a part of 128 as well as rotation. So we have to tilt our particular image as well as I have to scale the image. So whenever I have to match with this particular image, I have to go for some particular types of transformation. This is the basic important step when you start our programming with image fusion techniques. So what are these types of geometric transformation? So one is rigid transformation, FI, projective and curved or elastic transformation. Like there are many transformations are there. I'm just discussing only few, just to have an idea at a glance that how the images should be matched. So if I just take the examples of rigid transformation. So here, this is the original image. There is a part of some scaling operation here. So there is a transition from initial state to the another state, as I just showed in the first example of my rectangular box. And here I had a part of the rotation, and if this part is completely rotated in the 180 degrees. So first of all, whenever you're applying a fusion techniques, first identify the images. Are they properly indexed? How the rotation part or what are the pixel levels you're considering? Anything, if there is a variation, try to apply the corresponding transformation so that both images are properly matched. The next one is how to apply the affine transformation. So affine, you can just see that, you can just observe here. This is the original image. This is the scaling transformation and this is the shearing transformation. Scaling in the sense, my particular individual pixel values, your size has been little bit scaled. So whenever it is a concave lens and convex lens, so when I just take from normal lens, my image is of one way. If I take a convex, naturally we can observe the variation. That is what the scaling transformation. So we just go with some particular operation like 2x plus 1, some value I'll just insert so that I'll just drag to the original scale. And second one, shearing. Naturally, that is completely disturbed image. With that image, even if I fuse it, I'll not get the required task. So this is the one where we have to take care. And this is the projective transformation, like whenever in the car mirrors, when we just observe. Actually, some part of the image is good, but some part will be stretched. Actually, we just go with some particular non-linear transformation, logarithmic transformations. Some part will be stretched due to misalignment of the cameras. So when this type of thing, this part is more visible and this type. Okay, you can also mention that there is a variation in the pose. If I take my frontal face, if I move like this, what happens? This side will be less and this side will be more. If I move like this, this will be more and this part will be less. Again, if this image, if it is fused with the original frontal image, there will be variation. So whenever these type of variations are there, I have to go for the projective transformations, and we are having different functions for the projective transformation, and we can go further there. And the curve transformation. So some part, like we have because I have taken a face because it is a very easy example, and later we apply for the other different sceneries or X-ray images or satellite images. So this is purely curve part where some part of the information, a circle eye has been moved to the curved elliptical eye. Some particular parts are stretched. Your curves there is a variation in the curvature. Okay, Gaussian curvature is generally our transformation part. Many transformations are there, curvature functions, curvature frequency terminologies were there. So if this type of things are there, Gaussian curvature function, inbuilt function is there in the MATLAB. With that, I can able to tune up to the required particular phase. So this is the curvature transformation. So finally, this is a part whenever I'm going for the fusion technique. So my image can be of any particular thing. I know the base image. So I'll just calculate the similarity metric. Structure similarity metric is one particular part to how much extent your original image is tuned. So if that particular value, so original image, we'll observe and we'll just go for some transformations and identify some prediction points, important points of interest, and apply the transformation. And these two, once this part is transformed, we'll just find the similarity metric. And if that condition is satisfied, I go for the new transformation and I go further. Fusion techniques, whatever I want to impart it, I'll just go further. Otherwise, if that metric is not up to the mark of what I had considered, I go apply the another transformation with just taking some scaling factor. First time I had taken 5x. It has not met the mark. I just reduce to 3x and go further such that my metric will be satisfying a particular scenario value. So once this part is there, I'll conclude that whatever the two images that I'm considering, they are matched each other and I can perform the fusion technique. So coming to the fusion technique. So whatever the before scenario, I had just given a basement that when you perform a fusion, we have to follow these certain rules. Then the technique, whatever I am imparting it, will be attaining the required result. Many different fusion techniques are there, and these are the basic techniques. And in the present scenario, we are combining 2-3 techniques in different manner at different structure level also. So first is multiplicative algorithm. Generally, what we do, no, I1 and I2 are there. I1 into I2, I1 plus I2, I1 minus I2 are the general scenario of mathematical representation. So it has been started with the fusion in the same scenario. And the principal component analysis, which is a very beautiful algorithm that we'll discuss for the today's complete lecture. Another one is HIS, color transmission techniques. Fusion technique based on high pass filter. As we know, high pass filter means there is a sharpening filter. So using that particular technique, how we can do? And bravery transformation is very, very important part. Color related technique, wavelet fusion technique, and many more. So this is the overall scenario of the complete level of abstraction where you can perform the image fusion methods. So whenever I'm doing the image fusion, we had an image. I can perform at pixel level, I can perform at feature level, and I can perform at decision level. So whenever I'm just taking a pixel level, that is image transformed into the matrix, everything will be in terms of pixels. The methods which are related are color related techniques, statistical methods, numerical methods, and feature level, again PCA, segment fusion, and some LS theorems. And decision level also, expert system, neural network, and fusion fuzzy logic, so on, they'll be implemented. So why I concentrated here is, whatever the topic I'm discussing, that is principal component analysis, that can be applied at the pixel level as well as at feature level. But pointing that the fusion part, I can implement at different levels of abstraction. That is, if we observe, I'll take one or many images. The fusion can, because this is the general scenario of any particular implementation of image processing. That is, I perform the fusion. Later, I just take the feature extraction technique. Later, I go for classification. Then I come to the decision making scenario. So if I just observe, the first part is pixel level fusion. I can fuse the images at the pixel level. Second part is considering many images. Individual image, I take the feature extraction, and later I'll fuse the feature extracted images, that is the fusion level at the feature level, and later I go for the classification and decision making. At last, this is the higher end of the level where all the CNNs and DNS where we'll be using. That is image, we'll take the feature extraction, and also I'll perform the classification. After the classification, I go for the fusion technique. That is, after obtaining the output of some particular image using TAM technique, seeing the images, I'll mix the particular segment. So as for the application and as for the quality level, I go for this type of representation of the image fusion. So this is about the complete image fusion technique. And image restoration, we just observe the images. So we are saying fusion, but where these will be used? Fusion means we had a concept of mixing or combining two or more images. So here you can say in the image restoration, restore the image. So whenever we go for restore image, we say Wiener filter or blind restoration methods like that. These are the concepts we just consider. That is, my image is degraded by some particular and originality has been lost. I go for restoration technique. If we observe here, the first image, upper part is completely blurred, and second one, lower part is completely blurred. So I have to go for some particular filtering technique and identify which region is sharp and which region is blurred. In the particular blurred part, I have to go for the restoration. I should not do the complete restoration for the first image and second image equal. First image, I have to go with the restoration process considering the area of the region or region of interest. And second one, in this region of interest, I have to apply the transformation. So after that, when I combine it, if we just observe this complete image we had obtained, which is not having any blur either in the upper part or the lower part. Another restoration, this is the one where a Spider-Man image where we had an additional black color rod like this. And this is the one which had a black color rod. So my part is only removal of that one. Again, removal is not unique. For first image, I have to identify using some particular correlation matrix. I have to identify in which region has an abstraction, which is different from the other one. That abstraction part with image subtraction, I have to go further. And again, here the abstraction is completely different in the other area. So these two I have to remove and I have to combine it. This is one way of performing the image restoration. And the other one I'm just calling as image mixing. So restoration is we are removing the unwanted or degraded image due to blur or some extra additional parts, making it out. And this is the what we just go in the photography parts. Like two or more different images can be fused to create a new image which carries more information. Up to now, I just pointed out that only one image from two different sensors, a same image at different levels of time. I used to mention it. But this is the additional part of the fusion feature. Like in photography, right now we are enjoying different types of videos and photography styles. That is one scenery, another scenery. I'll just use the mixing technique so that we just observe the back of two sceneries. So this is one mixing example. Another mixing example, especially for sports. What is the way of identifying the path of the delivery and all the things? This is the combination of a person running at a particular instant, a long jump or any particular thing. What is this parabolic representation in complete scenario? We can able to identify. Even the cricket part, they'll just say, whether it is out or not. They'll just identify of wicket is. So there they go for the mixing. They just combine. So they take the video, but they make into slides of frames and take a different instance and go for the mixing technique. So whenever they take the frames now, naturally our image is degraded some particular blur effect. The sharpening is little bit more. So there they mix and go for the image fusion technique. So this is the basic practical example. And last one, image morphing. So I had gone with image restoration, image mixing, and image morphing. So morphing means two different phases or a particular, we can just say that actually morphing phases of two different persons. So we had just taken some mask and old Italian or Greek mask and we just obtained a morphed image. I think this will be more appreciable where this is the practical part where you want to mix two different phases of great celebrities. We got a new face. And especially many projects can be done with this particular morphing, like identifying the children face cuts, is that belong, how much extent they are belonging to father and mother or grandparents, like that. To some extent, some projects and research is going on this particular concept. So this is the part where I had just given all the basics, how to perform image fusion and applications, and fusion mentioning in different scenario with restoration, mixing, and morphing. Apart from that, I can use for different applications. Even I just relate as my topic is PCA, but along with that, I'll just discuss 4 or 5 papers with the combination of PCA, how the development has been improved also. I just go at the particular last. Now the starting part of the thing is principal component analysis, which I just mentioned a particular line like this. So whenever PCA, the other name for PCA we studied in our image processing is hot link transform or KL transform. So it's all related to the eigenvalues and eigenvectors. Partially, we are more habituated to eigen and eigenvector. So dimensionality reduction. When I say principal component analysis, dimensionality reduction is my main task. And 90% we say PCM is compression. So how to reduce? So how this will be used in the fusion techniques, step by step, I just go with small examples. First I start with a small example, later I'll just enter into the image. On the image, if I impart it, how we'll be getting the corresponding output also, I'll just leave one by one. So these are all the normal definitions which I discussed for the image fusion. And here I just want to segregate that. So in the remote sensing, machine learning, computer vision, identification has become overcome. Like we are identified, but in the many fields we are finding many technical difficulties. That technical difficulties first is size, memory. Right now, because of our VLSI chips and other things, memory size has been increased, and we are dealing with terabytes of the things. Implementing neural network based programs and all the things become easier. But 10 years back, it is not like this. So maximum we used to develop our algorithm based on PCA and SVM. So these both two are highlighted ones, and extended PCA, hierarchical PCA, kernel PCA, like that we used to go. So memory is the main requirement, and many technical issues we follow. So what is that we just observe? Starting with principal component analysis. It's a powerful technique used in data analysis, particularly reducing the dimensionality of the data sets while preserving critical or crucial information. And it does by transforming. So what is this? So generally we say, no, time to frequency conversion and frequency time conversion as a scenario for our signal transformations. So here, whatever the transformation we are doing, we are transforming original image, that is original variables, into a set of new uncorrelated variables, which are called as principal components. It is also just like what we are doing in our signal Fourier transform, Laplace transform. Our terminology is from time domain to frequency domain. But here our point is concentrating the original variables into set of uncorrelated variables. So what are those uncorrelated variables? All the things we just see step by step. But what are the key aspects of PCA? So if I just talk with the key aspects, as I told, principal component analysis means dimensionality reduction is our mind is set to the dimensionality reduction. So it helps to manage high dimensionality data set by extracting essential information and discarding the less relevant features, simplifying the analysis, which is again meaning of compression. Even compression also, I just go with similar definition. I will be removing the redundant data and extract the required data. And the other part is data exploration and visualization. Visualizing the data, that is, it plays a significant role in visualization, aiding in uncovering hidden parts and insights. So in examples I'll show later, which are uncovered. Physically, we just observe, no, in that image, nothing is visible. But if I highlight and take those components and place in the proper manner, you'll be identifying that some person is hidden near a tree. So we can be able to identify some hidden patterns. And it is purely the main advantages we can do easily. That is, it's a linear transformation. So it performs linear transformation seeking directions of maximum variance. So this is purely related to the statistical part. So variance, always my comparison is with reference to variance. Next one, feature selection. Apart from compression, I also just take this one as for the feature selection and use for the next upgrading part. Data compression, preserving the most relevant part. The next one is even principal component analysis. I can implement for clustering as well as for classification also, highlighting the underlying structure. And main advantage, as I just coded, linearity, computational efficiency, as well as scalability for large data sets. Whenever your data set is very, very large. So you can just, using this one, you can reduce the size of the data set and you can use for the typical application of classification, so on. But along with this, naturally, we'll have some limitations. The first one is it assumes data normality and linearity so that there will be some loss of information. Okay, this is the basic PCA. Later, we had developed some kernel PCA or combination of several different transformations. We just try to improve the loss of information. And the matrix requirement, what we just use it, the main requirement of performing the DCS is with the symmetrical correlation as well as covariance matrix require numeric and standardized data. I don't want approximation data or random data. I want a standard data to perform any particular task. And here the basic key factor for the principal component analysis is eigenvalues represent the variance magnitude and eigenvectors indicate the variance direction. So any particular image or any particular point, we are more constrained to the magnitude and direction. Generally, phase and magnitude is the final output of signal or an image. So this PCA will be very much particular that represents the magnitude variance as well as the and indicates in which direction if you move, more number of components will be assigned so that I can choose that direction. So the way we are moving. And lastly, the number of components that we are chosen are eigenvector computed. So PCA means eigenvector computed matrix feature model will be developing it. And most important advantage of PCA is when the data size is compressed, so as well as the dimensions are altered, there is no much loss of information at the output image. A slight change will be there, but that is not up to the requirement. And whenever we impart in the fusion technique, it is applied with weighted average of images are to be fused. And eigenvector related to the largest eigenvalue of the covariance matrix will be used to obtain the appropriate weighted of the source and computes, compress, and best description for the data set. And lastly, like if we just go for any transform, fast Fourier transform, DCT, Hub transform, hard transform, we used to say kernel or basis vector. Even PCA was also having the basis vector. So that basis vector, based on that, your data will be varying. So generally, I consider 10 images. From the 10 images, I develop a model vector or a feature vector. And this feature vector multiplied with again image 1. So you'll be getting a new image. So that is moving with reference to the feature vector. Whenever I say basis vector, if it is a DCT or your Hartley transform, hard transform, what I'll do, my image and multiply with the basis vector to obtain the new image. In the same manner, in the principal component analysis, I'll develop a basis vector, which is nothing but my correlation model or PCA model. Once I develop that model, no, whatever the image I'm multiplying with this basis vector, I'll get a new image. And that new image will consist of your size is reduced and you'll have more relevant data. Unwanted data is removed. That is the basic advantage of PCA. And because right now I just given some introduction to PCA. Before I had given the introduction to image fusion. Now I'm more dedicated to the how image fusion will be implemented using principal component analysis. So I go with an example of PCA step by step, but little bit I want to give some awareness that how we are fusing it. What are the techniques we are implementing? And this is the basic building block. Whenever we just draw input, transform, output like that we mentioned, no? In the same manner, I just consider registered source images. Now I'm saying registered source images. Can you tell me what is meant by that? From the before slide, I've shown 4 boxes where there is the indexing is not proper. There is a rotation or shearing and all the things. So when I'm saying registered images, both images are properly aligned. So do whatever the things before in the pre-processing. So before going to the fusion, my images should be properly aligned, properly indexed, and properly placed. So that's why I use the word called as registered source images. So these images, I go with, I implement principal component analysis, which is the algorithm which I'll just go shortly. And later, whatever the feature vector that I'm getting here, again, that image I'll be multiplying with the P1 and P2. What are the P1 and P2? I'll let you know step by step. And later in this part, because as a starting I mentioned, we may multiply or subtract, add. These are the basic methods in the initial state of the image fusion technique. In this particular process, simply I'm adding 2 images. So pixel of first image is added with the pixel of second image. But the pixel of first image with P1. These 2 are multiplied. So we'll be getting a fused image. So based on this, first, when I'm considering, because all we are talking with reference to images, I consider only the image data. So my image I1 and I2, both will HMS 128 by 128 or 256 by 256. Both should be of same size, are arranged in a column vector and their empirical means are subtracted. What is this meaning is, whenever I'm performing image processing applications, in all the applications, I just like a matrix and like matrix, I go further. But here, this is purely statistical based data analysis concept. So my image size of 1 by, that is m by n, I turn into 1 by ml. That is, suppose 4 by 4 images there. So I just turn into 1 by 8, 1 by 16. So as a column image or row image, I'll be specified. Then I perform the principal component analysis. This is the first part. And later, as a part of the PCA, first we'll calculate the mean. And later, these particular values with how many dimensions we are representing that I perform. Later, we calculate eigenvalues and eigenvectors. And whenever I'm just calculating the eigenvectors or eigenvalues, I'll consider, suppose we are having 10 eigenvalues. considering all the 10 eigenvalues and performing the same task is again waste of time. So there is no reduction in the dimensionality. So I consider first 5 or first 3 eigenvalues so that from those vectors I'll extract the required output. So instead of 1 by 10 features, I'll reduce to within 3 features itself, we can able to represent the image in the proper sense. And later I go for the normalization techniques. Normalization technique, and later I'll fuse with that block diagram what I had mentioned of P1 I1 plus P2 I2. With MATLAB code also I'll just make you to do in that particular manner. So this is the basic principal component analysis part. If we just observe here, roughly I'll tell so that step by step analysis I can move it. We're considering 2-dimensional data exponential component analysis. We are developing 2 new dimensional data set, 2 directional set E1 and E2. Among this E1 and E2, in which direction your corresponding values are more correlated, where your variance is very, very less, that I'll consider as a main principal component. And the other direction where my variance is very large, I can able to neglect. Implies a simple example, I'm taking 2-dimensional data into 1-dimensional data. How it is, that is, we just observe this is x-axis and this is y-axis with x1 and x2. And I'm having some particular points like this. X1 and x2 are the features. I'm having some data set with example 1, example 2. We're having 4, 11, 8, 4, 13, 5, and 7, 4, 2. We all agree that this is the 2-dimensional data. Now my task is, I'm saying the dimensionality reduction. Means 2-dimensional data is reduced to 1-dimensional data is my target. First I'll explain about this one. Later I'll explain with reference to images, considering n number of images, how it is reduced step by step. Because process and mathematical terms are similar, so I feel this will be a little bit confident for us in understanding. So once I have taken this particular feature, we are having totally 5 steps in the principal component analysis. First step is calculation of mean. So I'll calculate the mean with first I'm telling you the data. We can analyze the image with EX1, X2. It is a generalized one. Later the same thing, EX1, EX2 are then I1, I2, I3. Image 1, image 2, image 3, like that number of images you can able to consider. But main concentration is I'm just taking 2-dimensional data here. Later I'll extend to n-dimensional data. So this is pure a mathematical base, a simple mathematical example, like everybody knows about this one, but connectivity I just wanted. So I just calculate the mean of this one, and when I calculate the mean, so this is x1 and x2. So my particular point is 4 and 11, this first point, 8 and 4, and this is 13 and 5. The other one is 7 and 4. So these 4 points are distributed in this particular manner. So my main motive is in x1 and x2, if you observe the variance of this one, if we calculate the variance, no, all directions are equally distributed. It's not like that my variance is near to x1 axis or variance is near to x2 axis. Is the concept I can't able to deliver it. So my main motivation is and represent the PCA is separately, it's different for each image. Image to image data set to data set. Our particular component, principal component direction will be changing according to the type of the data set, whatever we are using it. So here we are calculating the mean across this particular point. And my main intention is based on these points, in which direction, if I choose my particular axis, so that all these points are correlated nearly, so that the variance is very, very close to each other. So that is my main intention. So first step is we are calculating the mean. After calculating the mean, second step is calculation of covariance matrix. Actually, I should say variance of x1 and variance of x2, but generalized we are mentioning it. So if you calculate this one, so one more thing what we can able to identify, if your diagonal matrix variance values are larger and covariance are small, whatever the assumptions that we are assuming it, less number of reductionality can be done. But if the values are equal and even covariance of x1 and x2, x2 and x1, all are having similar values, 0.9, 0.8, 0.7, 0.5, like that means compulsory you have to go for the dimensionality reduction. So usually I go for the diagonal whatever the diagonal elements, if they are not dominating the undiagonal elements, naturally dimension and reduction is required for me. So this is the basic formula for the covariance. In type of images, we just X transpose into X. And this is the covariance with reference to X1 and X2. So this is the first one variance formula. And this is the covariance where you calculate accordingly. So we had the data right now, the image data mean as well as the covariance value. And covariance of X2 and X1 are equal to covariance of X1, X2. And covariance of X2, X1, we are calculating all the 4 parameters, probably 3 parameters in this particular scenario. So once we had calculated the covariance values, this is the covariance matrix. So my data available is this one. I had data, mean I had calculated, and we had developed the covariance matrix. So later I had calculated, I go for the calculation of eigenvalues of the covariance matrix. So whenever we are going for the eigenvalues, this is purely mathematical background. So whenever I go for the covariance matrix, we find the characteristic equation of the covariance matrix. The characteristic equation is determined with determinant of covariance matrix of lambda I, and I just find the roots of the equation equal to 0. The lambda square, in this case, I got some quadratic expression of lambda square, some lambda. So equal to 0, I just obtained two values of lambda 1 and lambda 2. So later, I just, once we had my covariance, covariance values, I just substitute the covariance vectors. I just compute the covariance vectors. These covariance vectors are represented U1 and U2. And you observe that here we are having lambda 1 and lambda 2. So these two are covariant, I can call as eigenvalues, but preferably I go for the highest eigenvalue, the value which is having the highest eigenvalue. For that one, the corresponding eigenvector, if I found it, my intention is nothing but dimension and reduction. If I take both and if I do the purpose, we'll get it, but the concept of dimension and reduction doesn't occur. So here, I'm just taking the first one, like we had U1 and U2, whatever the values we had it. Lambda minus I, we just substitute S minus lambda I into U. This is nothing but the expression which we are leading it. And the eigenvectors are calculated in this manner. So whatever the calculation part we had on U is equal to U1 and U2, we related to some particular variable T, so that we had a relation that U1 is equal to 11T and U2 is equal to 14 minus T into U3. So that your eigen vector, that is 11 and 14 minus 11, but this is not the complete eigenvector, I can say. So to compute this eigenvector from U, before directly substituting the value, I go for the normalization. So what is the normalization is nothing but finding the square root of 11 square plus norm of that particular value, so that your eigenvector is represented with the corresponding value with U1 and the corresponding value. So if I'm substituting lambda 1 here, this is the first eigenvector. If I'm substituting lambda 2, that is the second eigenvector. Because it's only 2 dimensions, I'll get 2 eigenvectors. And even because before I had term how to calculate this value, similarly, if we consider lambda 2 here, in case of your lambda 2, I'm substituting U2 here, you will get another value with this particular value. So eigenvectors for E1 and E2. Up to this is the part of mathematics what we had done in the before sessions. So here, once we have done, what is my main task? Computation of principal components. So here, to compute the principal component, whatever the eigenvector that I had it, because here I had chosen E1, among the 2 eigenvalues, lambda 1 is having the larger value, lambda 2 is a smaller value. So which is saying that lambda 1 is having good variance with reference to the data points than with reference to the second data set. So even if I neglect the E2, large variance doesn't affect for me. So I'm just taking all the related data with reference to lambda 1. So I just take E1 considering the first eigenvector, and actually, frankly speaking, we can just put our actual data of X1 and X2. But we are just again subtracting the mean of that one. Whenever we are subtracting the mean, again our points, whatever the data set points are there, no, they will be all related and correlated to one set of cluster. So this way, once we multiply, I got the principal component value as minus 4 point some particular value. Again, just if you observe, if you just take E2 as your lambda part. So like this here, okay, I'll just go back once again. So here E1 with X1 cake. So what is this? This one X1 and this is X2. This is the first image. Suppose if I just take this one as the image, 4 and 11 are the corresponding features of that one. And what I'm doing, before I represented my image with 2-dimensional, that particular part when I'm implementing in this particular data set, the image E1 is now represented. I'm calling as image, but where is the data? If I want to correlate it, I'm just making it out. So that is represented with single value called as minus 4.30. Instead of representing with 4 and 11, now I'm representing example 1 with 4.3. Similarly, if we do for the next data of 8 and 4, we'll get one value. 13 and 5, another value. 7 and 4, we'll get another value. So this is the part. So our 2-dimensional data, now what we are doing, we are representing the 4 different data sets or 4 different examples, or little bit higher, and I can say 4 images also, I1 and I2 like that. So you are representing 2 sets of pages. I'm representing with single feature. This is the base for the representation of principal component, because I had considered only first principal component here. Second principal component, if you just observe also, the values whatever you are getting, no, they are very, very 0.087 like that I'll get it. Even if we consider also, they are very, very smaller. Now, what is this analysis? What is the geometrical mean of considering this one? This is the figure which I just quoted in the start of my problem. That is the corresponding data sets taking the mean. Now what I'm doing here, the values, whatever I got it. So if you just observe the before part, I had just try to remember these values, minus 4.37, 3.7 like this. Now if I'm just imposing these values, so to impose these values, what I do, I just consider the mean. For everything, mean is my centroid. So from this mean, if I just take some axis like this. So if I'm just draw a line here, this is my first quadrant, second quadrant, third quadrant, and fourth quadrant. And the values, whatever I got it are some minus 4.7 like that. If I just impose those particular values and draw the particular, if I just take a plus line like this and impose that particular values, these values are almost fixed in this particular direction. That is, I just mentioned. Here, E1 is there. What is the value of E1? 0.5 and minus 0.83. Is it? So 0.5 and 0.83 comes under the fourth quadrant. So here, the direction is represented in this way. And the other eigenvector, whatever E2 is there, that value is 0.83 and 0.55. So it is pointing to the first quadrant and moving in this particular direction. So here, if you observe my particular points, which before I just quoted as this is a combination of what the complete analysis is. Whatever the points 4, 11, 7, 4 are all them. I'll just take the masterpiece of my axis to be E1. And first of all, I'm mentioning I'm not considering the E2 vector. I'm just taking on the principal vector as E1. The reason is if we just take the points, all these points are moving towards only in this direction. The variance, whatever we are calculating, they are almost, they are very, very near. And if you just take the direction of E2 here, my points are largely distributed. So that's why, that is what we're doing. Instead of distributing the broader area, we are just saying that in this direction, I'm moving only in the straight direction of E1. I can get the corresponding path of the data sets of example 1, example 2, example 3. This is a part of the principal component analysis applied to the data. But the same thing I'll be implementing with the set of images. I think anything doubt is there? Yeah. Because this is a basic mathematical part. Now just consider the similar example taking on the mean, variance, calculating the covariance, eigenvalues, eigenvectors, and all the things the scenario is same. But once applied to the images, what is the change? That we'll just observe. Now I'll consider the images. Each image is having n features. Before my features are 2. 2 is reduced to 1 in the before example. Now I'm considering x1, x2, x3, a set of images I1, I2, I3. So I10 like that, I'll just consider 10 images, and each image is having n features representing some 20 features or 100 features. So I'll be representing my particular features, that is image 1. So image one, I'll be representing that. Actually, right now I mentioned that whenever image is there, how we are representing as a single line, which I told right now, my image size is of 10 by 10. I'll just represent as 1 by ml. It is nothing but 1 by 100. So that particular 1 by 100 that I'll be representing in this form. Again, another example, there is another image in this form, like that n number of images. And these are the features. That is a particular feature like x1, x2, x3, different features I'm just extracting for that particular image. And once if you understand, remaining process is similar to that particular, that is, I'll calculate the mean, I'll calculate the covariance matrix as usual as we had just done. But whenever I just go with the covariance matrix, diagonal elements are variance and remaining are covariance values. So if you just observe, naturally, like in the before also I told, before performing the PCA and after performing the PCA, if you just observe, my covariance will be highlighted in the diagonal after performing the PCA, pointing out that my direction of point is moving to the principal component or set of principal components. Because images, features, I can consider 10 features, only one feature representation. Again, there will be some loss of information. Maybe second, third, fourth axis is more important for me. So instead of representing 10 dimensions, I can represent with 3 dimensions or 4 dimensions. So here I'll calculate the covariance with the same formula, but it is 2-dimensional data. And we set up the determinant to get the eigenvalues. Now I just mentioned whatever the eigenvalues are there. Suppose I'm just checking it is a 10-dimensional data, I'll get 10 eigenvalues. Naturally, whenever I'm getting 10 eigenvalues, first what I do, based on the values, first I write in the descending order. So if I get 25, 20, 18, 15 like that, I'll just place it. And what I do, I discard the last eigenvalues and consider only 5 or 3 eigenvalues from the descending order, highest value only. That implies that highest value is more coincident with the required data than with reference to the large amount of data. Generally, our background is whenever I take the photograph, my eyes, nose, mouth will be having fiducial points, which are essential. Person to person, my fiducial points will be changing. But background is always same. Okay, there is slight variation in the background. If you observe t equal to 10, some background, t equal to 20, also some background, similar background, but almost it will be the same. That type of redundant data will be represented with single term. So that is the internal analysis of the principal component. So what we'll do is we'll just consider, that's why lambda dash we had placed. Actually, we have 10 eigenvalues, but I'll consider only 5 eigenvalues as per my requirement, such that whatever the eigenvector u1, u2, un, because I'm taking 10 data sets, I'll have 10 eigenvectors. And then we are making to 0, and we are taking normalized of that one, because once we have chosen the eigenvector of 5 features one, again I have to dump and create what is the actual for that image, how it is correlated. So that is represented by considering the norm, and we calculate the EI in this particular form. So how to derive the data set is, as I just quoted, eigenvalues from highest to lowest, we just consider lambda 1 greater than lambda 2. Maybe our choice may be different, but once it placed in the descending order, the first one will be the lambda 1, second one will be the lambda 2, like this. And from that, I'll choose only n number of terms. I just choose only p values. 10 values, I just prefer 5 values. Now your matrix will be p by n. And once we got these eigen values, the new data set, because again, I'll go back to my original matrix, m by n. 1 by mn is my scenario right now. So I just go with 1 by m by n, and the new data set, whatever I had used the feature vector m with 5 eigenvectors, that I'll multiply with your x1 image 1. I'll get a new image. Again, f multiplied with the second image x2. I'll get the new image. But what is this new image? Before, my new image is consisting of 10 features. Now that is old image is consisting of 10 features. Now new image will be consisting of 5 features. Okay. 5 and 10 I generally mentioned, but preferably we'll have 5,000, 512, like that. These are the features. So that is the part. Once we have the image of this type of features, no, what is the thing? We are extracting the required information and we are discarding the unrelated information. As in the high pass filter, what we say, only borders are required. I'll grab only the borders and discard the another part. So, but here border and other things are the important related, which is again related to the mean. Again, everything, the variance is more important for us. How our particular data points are varying reference to the variance curve, and we can have a new data sample. Once I had new images, no, I can go for the sampling, mixing, or fusing anything. So what we are actually, can I say transformation? We are transforming uncorrelated data to the correlated data. Because my data points are spaced randomly. Maybe you're sitting at different places. Once the lecture starts, all of you will be coming and clustering to the nearest benches. So in the same manner here, we are just taking the wanted data to be related to the near one. Unrelated data, we just throw it out. That's by discarding last lambda values. Okay. So this is about the basic concept of principal component analysis analyzed for the images. Now, once we had these images, what is our criteria? Because my topic given is image processing, how it is fusion applicated with the PCA. So starting with that one, the small MATLAB code I had just done. Afternoon, I'll just make you to do that particular programs also. I just brought the database of different sets, and you may just vary. Maybe I'm using plus, you may use some other particular transformation, and you can do, because the anonymous choices will be there, and we can implement it. So up to now, I think it is clear how we got the image, a new image, before image and after PCA transformation image. I think everybody understood the PCA image. I can call it the eigenface or eigen image also. Now coming to the small program in the MATLAB. So generally, I have given some two different images and I'm plotting. This is a very simple image. But how PCA is implemented is I'm using covariance. Em of column means what is the thing? All the things like MN, rows and columns are represented in single column vector. So we are calculating covariance EIG. EIG of C will be performing all the tasks what we had explained in the mathematical representation of my algorithm. Inbuilt function in the MATLAB toolbox, it will be performing. Now you are making a criteria that whenever I'm coding B, D, this as everybody know, B is your value and D is the eigenvector. I'm checking whatever which eigenvector is greater, because whatever the values will get it, lambda 1, lambda 2, lambda 3, we have to keep in the descending order. That descending order logic I just kept in this manner. Like if first eigenvector is greater than the second eigenvector, you perform your PCA, that is multiply your equation with this particular form. Otherwise, perform the PCA with the value of the second vector. That is, we may be having which eigenvector I have to consider that corresponding value, what I have to perform it. So this particular thing is just for the descending order, how to choose the lambda value to be greater. Once we had that particular form of the PCA, what I'm doing, the image fusion, IMF, we just called as a fused image. What I'm doing, PCA of 1 multiplied with image 1 plus PCA of 2 multiplied with image 2. So this PCA 1 and PCA 2, here if you just observe in the MATLAB, if I just put after, if you remove the semicolon, no, you can just observe that PCA will get like a diagonal matrix. So here PCA1 and PCA2, as I just mentioned, these are the new transformed factors. So when I'm multiplying with I1, you will get that one. PCA2 is the second transform factor. We are multiplying with the image 2. And here simply I'm just using addition operation for the fusion technique. So this is a part of implementation. And one performed in the MATLAB. I think this is not that much clear. But if you observe now, I had two images, I1 and I2. The down one is sharp image actually, and the upper one is a blurred image in the first image. And here the first one is sharper image, and the down image is nothing but it is a blurred image. And once I perform the fusion technique of simple addition, because it's the basic algorithm in the starting point, I got this one as both are having the cleared images. So this is the one. And second part, this is more clear for us. But this is not the simple PCA. I had used some particular combination of different features and some HPF, high-pass filtering techniques. Because only PCA is only a basic level of implementation. Along with that, I had to fuse the algorithms also. Not only fusing the image, I had to fuse different algorithmic representation. So this is the one image taken from one sensor. This is another image taken from another sensor. If you add it, this is the. So here I have to go for some intensity transformation, some illumination algorithms where the sharpening and all the things are there. So in each paper, what are those like? We can just go further, but using PCA only. PCA with a combination of different fusion, high pass and low pass filter restoration techniques, we had obtained this type of image. And okay, now we got the images. How you can say my image is better? So usually what is the concept we just mentioned is when you say accuracy or recognition rate in general scenario when you do our projects or research work. So here standard deviation is one parameter, is represented with this particular formula. Other one is entropy. Next one, fusion mutual information, that is fusion mutual information, that is FMI. This is also one standardized parameter. Another one is fusion quality index, FQI. So which is represented in this particular manner. And fusion similarity metrics. Generally, blurring and image restoration technique we call a structural similarity matrix, but this is related to the fusion metric. This is represented as fusion similarity metric. And so, okay, like this, we are having some different metrics and different papers. We are going for the different application scenario. Now I just taken some set of 6 different papers of recent journals. And there, as I mentioned, simple PCA like addition and subtraction at the basic level. Now we are in the real scenario. Different concepts have been arised like kernel PCA, or if I just say HPCA, H is nothing but my own algorithm of HOG features. Like I just mentioned that fusion can be applied in terms of feature level or addition level or extraction level. Anywhere I can able to apply it. So here they'll just go with the different combinations. So whenever we want a good research paper or research work to be done, just doing PCA, nobody will be appreciating because it's a basic work. Naturally, if we just see the algorithm, it's a pure mathematics. We're not creating any new from that one. The standard mathematics is there, we are analyzing according to that, and we are posing it. But coming to our application, so before I told, my image is one, before I have showed one PAN image and MS image, multispectral image, and your panchromatic images. So your sensors are in that way. I'll be taking different images, or simply if I just take an RGB image and by CBCR image. Naturally, when we do go for the type of conversion, so some part of feature extractions I can't do completely in RGB. Only if I convert to by CBCR and if I remove the luminance, CBCR will be giving more information or more data of the relevant quantity, especially your tumor detection or identification of any particular disease, like to identify the stroke, some pulse, more type of pulses like that. CBCR may be carrying more information. So, but again, if I convert it and work with only CBCR, it doesn't again, some other parameter may be missing. So what I'll do the analysis of RGB separately and by CBCR separately, get the analysis, and lastly I'll go for the mixing of that particular representation. Again, that is also fusion because I had given RGB and CBCR because of easy interpretation. So like that, PA and panchromatic images, it's like a by CBCR, but that illumination part again will just rescale and make into some scaling factor and rotate in that particular part so that my image identity from longer distance will be more sharper. But it is a costlier. The sensor, whatever I'm using from that one is little bit costly affair. And when you take a photograph of that one, take the print and all the things, it's a costlier affair. But MS images are quite easier. Like if you say X-ray and CT scan, nobody goes for CT scan image until unless your pain is more. We don't go for CT scan. X-ray is only X-ray, no? We just take because price wise or whatever the method that doing it. So here, whenever I just RGB by CPCR I had mentioned, in PAN images, analyzing the techniques of PCA, but only PCA doesn't work in the sense we are in the advanced stage of identifying more three-dimensional data or in depth of the concepts. We just go with the satellite images, They're going for the 5 meters depth of the object and identifying what it is and so on. So to go for the latest techniques, no, we just try to mix different techniques. One of that particular part is a beautiful paper which I want different application based. So before that, I just say that one is PAN image, another one is MS image, and different feature techniques are there. And coming to the feature extraction techniques, as yesterday sir has given many techniques, I think so. So we're having local features and global features. Again, there also, if I take the global features, I take PCA features in some particular application. Extracting PCA features and go for another type of classification. I may not go for PCA classification. See, PCA, how much very important is we go for dimensionality analysis. Second one is we are going as a feature extraction as well as PCA can implement for the classification also. So I can use as a multitasking agent, but as per my application, I go for that one. And second part is whenever I'm just taking the feature extraction, olden days or not, I should not say olden days, previous works, we only concentrate with the local features and extract and we go further. Or I just go for the global features like HOG. HOG means histogram of oriented gradients, or this one like PCA, LDA. These are all the global features. So from the global feature, overall, you can able to see. So what are the things are in the PCA? I'm just saying all the values are distributed and they are segregated. I'm mentioning. But what is happening to this point in a matrix? I1 of 20, what is happening? We can't able to tell. But in the local features, you are just taking addition or average of successive pixels or taking the mean of complete like a 3 by 3 matrix. If I just take the mean and just keep as a single value, this is also one type of feature extraction. There you are more specific at the pixel level. These you are more specific at the overall resolution level, I can say. But both are equally important to extract the information. So what they had done is for the panchromatic image, they had gone with the self registration. SURP, like LGRP feature. SIFP shift features are there. These are all comes under local features, and each is having an algorithm of a set of equations where we go undergo with some iterative part also. SURF nowadays. SIFT and SURF both are dominating because one paper says that I go for SURF features, another paper says that with the same content, if you just make SIRF now, it becomes a paper. Or I say that instead of SURF and SIFT, one you do SURF, another you do PCA. Means mixing local and global features, you will obtain a new feature. And this is all trial and error. I can't say that because we had a program, already existing program is there. To write an algorithm step by step is over right now. Now our part is using one algorithm from the another algorithm and I have to mix it to get an efficient output. Ultimately, what is my target? My accuracy has to be improved. In one particular scenario, for that particular data set, I got an accuracy of some 84%. Now, make your own analysis such that your accuracy, if it is increased to 89%, we will be appreciated. So in what way we'll be going? So based on the type of the image also we have to consider. As these are satellite images, for these images, we just go for the local features and MS images, I'm going for the PCA transform. That is global features. So based on the type of the images, we are just extracting it and later they perform some histogram matching. So we all are aware of histogram, like how many times a particular value is occurring in the particular image. There a matching technique with PAN image one, that is I just made that image with histogram matching. There histogram matching again, histogram equalization and histogram specification. So specification is the particular part where I can able to normalize my image in the proper sense, because there what I'm doing, I'm using local feature extraction. So in the local feature extraction, your points may be distributed in different uncorrelated form. So once we just do the histogram specification, all the values are specified in the proper manner. Then again, I perform one. Here they perform some RBW transform. But my intention is you take the same image and same block diagram, but you use, because many transforms are available in our toolboxes. Different types of transforms are directly we just PCA of, even I had just given covariance or eigenvalue, but simply in the MATLAB, PCA of I1 and whatever the values we just specify, immediately you'll get the answer. Because of technology development, many inbuilt functions are there. So here, they just made some, again, extraction. They made, again, principal components of first principal component as well as another principal component they had analyzed. First principal component is, don't assume that in this paper, because when I had explained first principle, I'm only first one. But whenever they go for the experimentation, they go for set of some particular, because there we may be having 1,000 features. So among these 1,000 features, I select 30 features as the main principal component, next 30 features as the another principal component. 30, among 1,000, we are just taking only 60 components. So again, it is a part of reduction, but it consists of maximum information what we had it. Of course, there will be a loss because 1,000 we are representing with 16 features. There will be some amount of loss. So these are again gone with some RBW transform. This is all region based transforms, like the hub transform. In the segmentation part, we used to go for some type of transformation. So in this paper, they had gone with some region based wavelet transform. So naturally, in the wavelet, we have low frequency, high frequency, some differentiation parts. So for the satellite images, we need both. In our typical application, for I say high pass filter output is sufficient, or in a particular application, even if I just say blurring, our image may be blurred. So whenever I take an image, directly I'll not, whenever you practical idea of what we'll have is, if my image is blurred, okay, use low pass filter and do it. But that is not the case. So what we have to do, no, we have to still blur it. So what I'll do, I'll just use first low pass filter. Means already it is blurred, but first trigger I'm making blur, then I'll apply the high pass filter. That is, if I had a dot with some particular blur, I'll make little bit noise to that one so that I can remove the noise in the proper manner. But what is the difference? Can you guess? What is the blur? I don't know. But when I'm adding the blur, I know the equation of the blur. I know the strategy. Is it decreasing graph or increasing a logarithmic or a piecewise? So what I'm doing, unknown part, it is like in the signals and systems, we say, no, I'm approximation one signal over the unknown signal. I don't know the unknown signal, but known signal I'm pressing it and I'm dragging it, orthogonality, which is the same thing. In the same manner, in the general scenario of blurring, directly if I use low pass filter, finish this blurring concept and all the things doesn't case. A blur is there, but I'll introduce a standard blur, maybe a Gaussian blur or motion blur. I'll introduce it, then I go for the reverse algorithm. So when I mix it, what happens? 25, unknown blur has some 25, 30, 40, but known blur is having 25 and 60. At least one is mixing with that one. So I just take it so that that part will be removed. 100% removal of blur is really very difficult. But what I'm doing, we are adding noise, but removing that noise in proper sense, proper transformation technique. That is the concept what we use it. So here, 90% what we say, no, whenever we had image, take only the sharpening image, neglect the blur image, like that we'll mention. No, we need any image at any particular time in place of fusion, because we are fusing to get required data. So here we are taking high frequency coefficients as well as low frequency coefficients for both the images. But one, I'm going for the local description technique. Another one, I'm going for the global PCA technique. So later, what we'll do is, I'll just take a combination of this one, high frequency, I'll combine with fusion techniques, and low frequency of this one and low frequency, I'll combine it. And the transform, what we used is region-based wavelet transform, they have used it. In the frequency domain, we are making all these techniques. Generally, we know that when we do in the frequency, convolution in time domain is multiplication in frequency. So my particular fusion techniques imparting in the real time, if I perform everything in the frequency domain, again, after performing the fusion, we'll come back to the original time domain. My signal will have very good SSIM. SSIM is structural similarity matrix. So to need my parameters in the more efficient manner, that's why I've taken this one as a first paper. Those remaining all like addition, subtraction, what is that, like that we used to think. But here, this one, I'm adding the, what is the fusion part here? I'm just adding high frequency of MS and PAN images. adding the low frequency of MS and PAN image. One set of fusion has been done. Okay, how they are added again, I'll tell you in the another step of the papers. Okay, so this is a very standard paper consisting of many different scenarios. And once if we take this one, as I just put in PAN and MS image, you can take PET images and this CT scan images. One will be giving the muscles of the bones or the distributed, one will be the giving the complete skeletal information of the bones. So medical images where tumor or brain tumors and all the things, or lung cancer also. Before starting, I showed one particular figure pointing out some cancer point. Just my block diagram will be similar, but application of the transform will be different. Instead of sir, if I go for the medical images, no, I prefer local binary pattern, or similarly, we had a very good pattern called as local Gabor rank pattern. Actually, Gabor filter, generally we call as a Gabor wavelet, which is a beautiful wavelet. Like PCA is a standardized one. PCA is a basic thing, but it is moving in the very great application in fusion with different algorithms. In the same manner, Gabor filter, Gabor wavelet, which is a very highlighted concept. That Gabor filter as a wavelet concept and local Gabor, we had a logic for that one. Like take as if I say if I'm just taking image of 10 by 10, taking the average of first 4 pixel is one value. That is usually feature extraction. Local Gabor rank pattern also having some particular terminology how to consider in a diagonal manner. If you just go in that particular for the medical images, one local feature, one global feature, and extract high frequency like user transform. So the transform technique can be, we can start with DCT because DCT is the basic transform what we were habituated, or DCT, heart transform, any transform. Heart especially is used for detection, the tumor detection or identifying any small hole in the heart. There we go for the edge detection techniques. Their heart transform is really, even I used in my face detection. Starting I had done before recognition, I had done detection. Many were habituated ADA boost algorithm, that is a common algorithm used in the face detection. So there completely they go with the hard wavelet transform. So that is also having a very beautiful feature extraction technique. So here it is. So this is the one which I use the fusion. So one fusion is with high frequency components of MS and PAN. Again, when I'm just making MS and PAN, my starting analysis, that is my transformation assessment should be the proper manner, proper alignment, proper indexing should be there. Then the technique again, the different fusion techniques can be imparted. Like starting I had given and bravery technique. Many cases they go with that type of algorithm. And another one is you are mixing the low frequency. Later, I'm just performing the inverse, and again here using the PCA inverse transform, because here I use the PCA transform. Now again for the diamond, because we had a huge data, we are more specific to the narrowing the part of what is required of my interest. Suppose I have to identify where are the buildings from the satellite image, or more interest is I want to identify where forest fires will be there. So there only region of interest is more important to me. So that's why I'm going for the PCA. So in PCA here, my region of interest is identification of where forest fire area is there. So that's when I'm going for the PCA. If it is some other application, I go for something. But naturally, when I'm just going for the fusion, as I told, we are going for the medical applications or classification from particular thing. I'm more pinpointed to what I require. So that's pinpoint to some means my feature is only limited. So when I'm just having, if I take a photograph of any particular thing, many cases I have to give similar example. If I take a group photo, and if group photo is given to you, what is the first scenario? I'll see where I am. Maybe all the friends will be there, but first my view will be where my pinpoint is, how I'm looking, am I smiling or kept something like this? That is my intention. In the same manner, whatever the applications we just go with the fusion, we are pinpointing to particular application. Is that the tumor is there, the hole is there in the heart, or water area, or we are having a very good application like under the sea where we just highlight the fishery people go to this particular area so that you can grab more number of fishes, move in this direction. How they are extracting from the satellite images, doing all this type of transformation. They are highlighting that in that one they are least bothered what is the color of. They are only pinpointing where the fishes levels are. They just identify some crucial points of that particular fishes. Where they are located, they will be extracting it, and they'll just indicate the fisherman that you move in this direction, you can able to extract. So that is the part of this particular image fusion technique with reference to this paper, as this is related to PCA and red-black wavelet, RB wavelet. But red-black means usually that's purely related to region based. Red and black, some colors among many colors, we just specific to two colors. So that is purely a region based. Usually red-black wavelet will study image segmentation. So that is one particular application. So these are the results. Even I had the MATLAB code for all these things also. If possible, we'll try to implement it in the afternoon session. So they are implemented PCA along with PCA are only individual wavelets. Entire scenario. And they had combined RWPCA, and you can just observe the final output F is having more information and more clarity compared to that. Because these are satellite images, our identify, because before tumor means, at least we can say this is the tumor. That knowledge of satellite information, what is that? We are not that much particular, because that knowledge of coloring of watery areas, they'll just, they go with another scenario, like ERDA software will be there. We are using MATLAB, Python like that, no? For evaluation of the satellite imaging, they go for ERDA software. So that software will be automatic. Their point of interest is vegetation, water, rains, and all the things related. They'll have some specifications according to that. They go with according to that. And they specify, they calculate all the values. Before I had mentioned some table, assessment, FMI, like that, feature and metric values. Based on that, they'll calculate and decide, okay, today's weather will be like this, or after 5 days, the weather or occurrence of cyclone will be there. All these type of data can be analyzed from the satellite images. These are from different data sets, what they are having. And these data sets are available in the Google portal also. We can download that from the Google portal and we can able to implement it. And from the data what we had acquired it, we can go for the evaluation purpose, some clarity, entropy, cross entropy, and all things values will be done. And this comes for the finalization of selection of our what type of algorithm. And when we want to implement it, no, do the same part. Instead of using SURF, go for NCRP or change the image data set. So we can just create some. Maybe initially we may get 60% of recognition. Don't worry, initially we have to get 90% or 95%. If we get 40% recognition, we are successful. Because we know where we are done, what to modify into that particular thing, we can able to do, and we'll change our transforms. So they have used RB value. We may use some other transform and changes we can identify. So this is the part of first paper. And second paper, which I had just taken, because I have not mentioned anything. 10 minutes, okay? Fine, okay. Okay. Otherwise, on the lab, again, I just move it. So modified PCA based image fusion using feature extraction. This is very simple. Even I had the code we'll just do. And a little bit I'll go a little bit faster, because my intention is to share the ideas how to implement it. So image 1, image 2. And what we had done is I had done my image into 4 parts. That each part, I'll take the principal component. Right now, what we had done, 256 by 256 image, I had implemented PCA and I had done the fusion technique, addition or multiplication. Instead, this is a simple technique. 256 by 256, what I'll do, 64 by 64, 64, 64, 64. 64 pieces I'm doing. 164 and PCA 1, PCA 2, PCA 3, PCA 3. Later again, I'll take the average of that entire value and do the fusion case. This is a very interesting one where you can identify the fused blocks, and this is a modified PCA, because starting PCA, what I mentioned, simple PCA, just do the eigenvalues, you'll get the value added. This is modified, just making into parts. And the other one, which is very interesting, DCT. DCT algorithm, discrete cosine transform. So dividing the DCT, that's D is just for making into subparts. So here,
I had an image, I1 and I2, which I showed in the starting completion of PCA, some MATLAB output. So above image, if you just observe, this is blurred image and this is clear. And this is clear and this is a blurred image. I'll just mode 0 to 9 is the DCT and make into slices. Your image, our bit plane slicing we have studied in image processing. I'll just make the slice of the image. There apply the DCT for individual for the 8 slice. Again, I'll just go for some mode 0 to 8 rules. In the fuse, even there also bit planing, I'll just consider the first 6. The other 2 I can neglect it to extract the information. And later I'll go with the fusing with the PCA. Along with the DCT, DCT will apply for the bit plane slicing for the sliced image. And later I go with the PCA technique so that you can get the clear image. What is happening, I'll let you know. Here, what is happening? Yeah. I'll take the image. This is one of the bit plane. What is the difference? Can you identify? The negative image. All blacks are turned to white and whites are turned to black. So in the bit plane slicing, we'll get all the levels 0 to 8, first grade level, second grade level, like that. So even here also, and just like this, we'll just take some slices and we'll add it accordingly so that I'll get a clear image. So here one more thing is that where you may be asking, where is the blur and where is not blur, how to identify. You are showing one is blur, other one is blur. When you fuse it, it is there. So there also, we are going for some particular techniques in such a way. First, I'll identify the region of interest, like image properties, in props, in-bit function is there. From that image, when blur is there, almost all values are near. Suppose I had 200, nearby values 200, 201, 203, 204. This implies that my complete region is scarred. If I'm having 200, 220, 225, there is some variation. My image is having some clarity. So that is there we having some particular techniques to identify whether how much extent my image is having clarity. If blur is there, region where the blur is there. So in that way, you can able to identify one particular parameter. And this is another one where CT scan and MRI. I start with satellite image and normal image. In the CT scan image, we go for PSO means it is nothing but your swarm pseudo SW, which is again a beautiful algorithm. So we'll perform both PSO as well as PCA. And we convert into frequency domain and perform inverse transform and do it. Here I just go with a wavelet transform. So I just concentrate wavelet, as you know, low pass to what the decomposition level we consider. So that feature selection we'll do and go for the application. So as a wavelet and LGRP features are more useful for the medical imaging and tumor identification part also you can able to identify. But all these algorithms are with combination of PCA. Only PCA is not the highlighting thing. You combine a technique in combination with the use the latest feature technique combined with the PCA, your results will be more accurate. And this is one of the hierarchical scale, like pyramidal structure of the images, where it's a one type of wavelet. It's not completely wavelet. We just say a pyramidal model of the signal. We just decompose into several factors and we'll make the PCA. So here I just go with your P1, I1, P2, my same formula, but at each level I'm performing. Like I just mentioned, bit plane slicing, slice of 8 bits. So first slice of first image, second slice of first slice of the second image, PCA. Second slice of first image, second slice of second image, fused. After making all the individual slices fused, again I'll combine all the taking the average of that one. So it is one way. Like wavelet, this is also a pyramidal structure representing. So these are the typical examples pointing out with the fusion techniques. And the last one is PCA based with high pass filter. So high pass filter further sharpening. So this is also a beautiful paper, the latest 2022. So we go with different transformation with the different images and do the PCA as well as inverse PCA of that. And especially identification of the building. Actually, we are dealing with this type of topics in the projects in our next scenario in our college. So there we deal with all panchromatic and MS images, dealing with all these particular fusion techniques. So these are the particular data. Because as time is less, I can just stop here. Any more doubts?
Okay, thank you, madam. You are giving a wonderful explanation about the image fusion algorithms used on PCA. Now we'll go for a short break. The next session will be on 11:30. Right? Next session.
For giving me the